Alright, students, we are concluding the third part of three uh, review videos here on oscillations, waves, and sound. Let's get going with superposition and sound. First up, superposition. So the principle of superposition is basically when you have two waves that are coming at each other, then here you go, they both overlap temporarily and then they continue on. So they can both simultaneously be at the same point, and the displacement of that medium is the sum of the two of them together. So it's kind of a little wimpy wave, but when they get together, woohoo! Nice, powerful, strong wave, lots of amplitude there, but then as they move on, go about the rest of their lives. That's the principle of superposition. That sort of interaction is called interference. If they're both have positive amplitude or negative amplitude, if the direction of that displacement is in the same direction, then you're going to get what's called constructive interference, where like this one is going to build on top of that one. If they're in opposite directions, then you get destructive interference. And it might even possibly result in a temporary complete standstill of the medium. However, just one moment later, as those waves move away from each other, you'll start to see them take shape again. And what it is just they're both present right there at just that particular moment. In this case, it's 1.5 seconds. But then, 1 second later or half a second later, they're moving on. We can see them there. Interference is the term that we use for sound waves or any sort of waves when they're interacting with one another. If you have, say, for instance, two speakers and they're lined up properly in really awesome position, then their sound waves will be what's called in phase, and they will it'll sound even louder. However, if they're exactly in the wrong position, you get total destructive interference, and even though you have two speakers here, those waves are canceling each other out completely and you wouldn't hear anything out. Of course, in real life there'd be sound waves going in multiple directions, not just straight in a line, but it's kind of fun to think about. Standing waves, they're called standing waves because it looks like it's a wave that's just sort of standing still, but in reality what's happening is that there is a wave going all the way down here and then all the way back, and then there's another one going all the way down here and all the way back and forth, but those waves are hitting each other, and as they do, they're hitting each other just at the right time and the right form to make, at this spot right here, for the rope to be going up and down completely, and they're meeting complete peak meets a complete trough here at this spot here, and so this spot stays in perpetual non-motion. So this happens to be called a node. These are antinodes. Somebody asked me during a quiz one time, what about the endpoints? What are they? Well, they're endpoints. They're neither nodes nor antinodes. So that's a standing wave. Spent a lot of time talking about this because this is the basis for that high frequency response that we saw earlier in oscillations. It's also responsible for sounds that we hear. So we dealt with lots of graphs here. If we look on a string, we also mentioned boundaries, where when the wave comes along, hits a boundary and moves back. Something I didn't make a big deal about, but however, this is the case where if there's a discontinuity, say we have a thick rope going to a thin rope, then there will be a reflection back, but also there will be a little bit of that wave will continue on through the lighter, thinner string. It's possible to have different forms, different situations. We call them modes, different modes of standing waves. So this is mode 1, this is mode 2, and you say, what causes the difference? Well, it's the frequency at which you're sending energy or you're shaking this rope back and forth, and that frequency is twice as fast here for mode 2 as it was in mode 1, and 3 times mode 1 if you're looking at mode 3. And it's possible to calculate the wavelength if you just were sort of to continue on this continue graphing this and figure out, all right, well, this is actually half of the entire wave, and this is in this case from this point over here to this point here, that's the entire length. And you can derive a relationship between the wavelength and the length of the string there. And that's exactly what we did. We did mention the string sort of wants to or likes to resonate at those modes. Probably more technically, it's that you could be sending multiple frequencies down the rope, but only those that are at the modes are those that will persist. Everything else just sort of cancels each other out. This was a reminder that those higher modes are multiples of the fundamental mode. Those higher modes are sometimes called the harmonics or the higher harmonics. And this is just like I was saying, the resonance sees to it that only the frequencies to persist are those that make possible standing waves. And that leads us to standing sound waves, which is the sounds that we hear. Pressure changes back and forth, but then due to the air column moving back and forth. And if you have an open tube, remember that the air pressure is atmospheric pressure pretty much no matter what at the end of those tubes. So an open tube resembles a string that's tied on both ends, which is great because we can model that all day long. A closed tube, don't see too many of those, but it's possible. The end of those, the air pressure here can go up and down, it can change, and so you end up with standing wave patterns that look like this. And an open closed tube, at the open end, it's always locked in at atmospheric pressure. Meanwhile, at the closed end, it can be open. So you can draw those, and on your AP test or on my test, you may have to. So be prepared for that. This is just another picture of the same thing. We also talked about the frequency spectrum of sound, where human ears can hear everything about from 200 or 20 hertz all the way up to 2000. And so you can have different intensities of different frequencies. The fundamental, the lowest frequency that you hear, that's called the fundamental. Then you've got your higher harmonics. And you can have lots of different frequency responses we talked about. Now this is for dealing with vocal cords, and then the shape of your mouth sort of filters out some of those, and that's how you hear the different sounds of the different letters and consonants. And lastly, we talked about beats, which is anytime that you have two waves with slightly different frequencies, and they're both going, and for a time they completely line up because they're similar frequencies, but then because they're not exactly the same, then they get out of, or they're already out of phase, but they turn into complete destructive interference here for a little bit. And so when you add these two up, due to the superposition of waves, it's what happens with waves, you add them together, then you get a high constructive interference here, then destructive interference, then high. And what happens is actually you don't hear both of those sounds. You hear this sound a little bit quiet, then this sound again. You hear a single tone rather than two tones. And that's, this pattern right here is what you're going to see with beats. That's the beats phenomenon rather, and you would hear one single tone. So you hear a loud, then a soft, louder, soft, and the beat frequency that you hear, or the frequency of those beats, corresponds to the absolute value of the difference between those two frequencies. All right, that's going to conclude everything on oscillation, waves, superposition, and sound. Good luck. I recommend you read through these slides to maybe get a little more mastery, review through your notes, and good luck.